I want to start talking now about a couple of concepts. We're heading here toward uniform circular motion, and I want to integrate the idea or use the idea of Newton's second law of motion. Now, Newton's second law of motion states that force is equal to mass times acceleration. And the vector version of this, when we write force and acceleration in terms of vector, we simply get that the force vector is equal to the mass of the object times the acceleration vector. Now, keep this in mind because we're going to use this idea and apply it to uniform circular motion. So, oops, this is omega. It turned up really small. Okay, so Newton's second law of motion can be applied to the idea of uniform circular motion. Now, as an example, let's just jump right into an example. An object with mass m that moves in a circular path with constant angular speed omega has a position vector r of t equals a cosine omega t I plus a sine omega t j. Now, find the force acting on the object and show that it is directed toward the origin. Now, I want you to think about this function just a minute. I have cosine and sine, and they're both multiplied by the same scalar a. Well, you know, if I take a look at a circle, I can define a circle with sine and cosine. So this is clearly a circle, and a, that's going to have an effect on the radius, how big this circle is or is not. And omega, when we put it in here, omega will have an effect on the period. So between 0 and 2 pi, how far along the circle do I go? If omega is 1, then I'd end up with, between 0 and 2 pi, I'd end up with a full circle. And then obviously if omega was less than 1 or greater than 1, that would determine how long it would take to get a full circle, or if I have more than one circle between 0 and 2 pi. So this function itself should not be a big surprise that this is going to describe somehow a circle. So what I want to do is I want to find the force acting on the object and show that it's directed toward the origin. Well, what does that mean? If I set up an axis system and I have a circle, and basically I have this particle moving along the circle, hence uniform circular motion, then I'm going to have a position vector at any time t. And that may look something like this. So I want to find the force that's acting on the object, and I want to show that it's directed toward the origin. In other words, whatever force is acting on this particle as it's traveling along in this uniform circular motion, we need to show that the force is acting in this direction, heading back toward the origin. That's what that's saying, just to make sure that we're on the same page here before we jump too far into this. Okay, now I know that r of t, my position vector, is going to be a times cosine omega t I plus a sine omega t j. Therefore, the velocity vector, v of t, is going to be equal to r prime of t, which if I simply take the derivative of this, I will get, let me see, I'll have a negative a omega sine omega t I plus a omega cosine omega t j. So this is my velocity vector. Now the acceleration vector equals a derivative of the velocity vector, which, not to be too redundant here, but it's the second derivative of the position vector. This is going to be, negative a omega squared cosine of omega t minus, I'll have another omega squared sine of omega t j. Now remember, this is about finding the force. So we just found the acceleration, but what's the force? Well, force equals the mass times acceleration vector. So the force is going to equal mass times negative a omega squared cosine omega t minus a omega squared sine omega t. Oops, I forgot my I here. I forgot it here too. Hopefully you caught it. There's the I and there's j. Let me fix that just a little bit. There we go. Okay, so this is actually going to be equal to, I'm going to fiddle with this just a little bit, because what I'm seeing here is I'm looking at this and I'm thinking, you know, that looks an awful lot like our original vector here, or our original position vector. It simply differs by omega squared and these negatives. So if I factor out the negative and the omega squared, I'm going to have a negative mass times omega squared times a cosine omega ti plus a sine omega t j. Well, this is my original position vector. So force is my original position vector scaled by the value of the mass and the angular speed, and it's the negative of it. Well, if I take the negative of a vector, it simply goes in the opposite direction. So what I just showed is that the force vector is in fact in the opposite direction of the original position vector. It is the original position vector scaled by this value. So I could actually rewrite this as force is equal to a negative m omega squared r of t. This force that's acting in the opposite direction, this is actually referred to or is called centripetal. This is centripetal force. And just very, very quickly, as a very, very basic vector review to make sure you're totally with me what I did here. If I have vector, I don't want to use A, B, and I use R. It doesn't really matter. I'm going to use, say, vector R, and it's this vector right here. Whatever that is, there it is. If I take a scalar and I say 2 times vector R, that vector would be exact same direction, but twice the length. So if that's the same, then let's say that's twice the length. If I take a negative 1 and I multiply it by R, that's the same as negative R. It's going to have the exact same magnitude as the original vector, but the negative makes it go in the opposite direction. So it's going to be like this. Pretending that I drew that, so this is really opposite in direction, exact same length as R. And that's exactly what I did right here. And remember, I just circled that negative. It's not a theta. Let me change that. Because this is the negative of my position vector with more scalars on here. So if I had a negative 2R, that's going to be this vector, which is twice as long as the original, but the negative is going to make it go in exactly the opposite direction. And that's all that I'm saying right here. is that because this negative is going to take r and go in the opposite direction, and the length of it, the magnitude of the force, will depend on a combination of what this value is, the mass, and the angular velocity, and of course the magnitude of the original vector.